go. All right. Cool. All right. All right. So first thing first, just as a follow-up of our discussion on Monday regarding hackathons. So somebody told me, one of my students in cisp 310, she's also taking classes at Sac City. So they're going to have their own hackathon in April. I don't know whether they have all the details worked out yet. So let's check it out. Sacramento City College Hackathon. I think they want to call it a codathon or something like that. Let's see. And I know they are doing it in the capacity of a student chapter of the ACM. So if I look up ACM, which stands for the Association of Computing Machinery, that's kind of like IEEE to electrical engineers. ACM is kind of like a really established professional organization. Okay, so let's check this out. Come on. All right. Nope, doesn't look like they got it updated yet. Nope. So if I find more information, I'll let you guys know, because I think at least a few people in this class, seem interested to go to a hackathon. And this one, since it's organized by Sac City, it's very local, and it's going to be in April. So for those of you who want to participate, you can kind of plan a little bit ahead of time, find your buddies to go with you, yeah. So I think that would be kind of cool. And let me see if this one has anything on it. Nope. Okay. No additional information available yet. And all right, so let's go ahead. So now what we will do today in this class is to continue our discussion of resolution. So we're trying to combine all the three things together now. Okay, we're trying to combine CNF, conjunctive normal form, which is a quote-unquote universal way to express Boolean expressions, but in a very specific format. Okay, it's basically it's a gigantic AND of a bunch of ORs, but what you can have in the ORs is very restrictive. You can only have constants, negation of constants, variables, and negations of variables in the ORs, but then you can combine the ORs with and AND all of those OR terms together. Okay, so that's CNF. The second ingredient that we have is resolution, which is, for the most part, a very mechanical process that basically says, if you have one expression that is not negated in one OR, but it is negated in another OR, and then the two disjunctions are ended together, then you can concatenate everything from both expressions and eliminate the one term that is negated on one side and not negated on the other side. Okay, that's resolution. And then the third ingredient is proof by contradiction. So proof by contradiction says if you have a bunch of expressions that are known to be true, we call it psi. You have a theorem that you want to prove, we call it phi. And you want to prove the theorem is the result of psi. Then what you need to do is to negate the theorem, combine it with everything that is known to be true using a conjunction, and then show that that will lead to a contradiction. Okay, if it does lead to a contradiction, then the theorem is actually a consequence of the known facts. Okay, so those are the three ingredients. So what I'll do is I'm going to give you an example. Okay, so instead of just talking about it, let's go ahead and work out an example. And I'm going to use let's see, I'm going to use Zernal, so I can actually write it out like on the piece of paper. So view, zoom, page width. Okay. All right. So let's go ahead. So things that we know to be true. Okay. So let's go ahead and work with psi first. So in this particular case, psi is defined to be the following. We know that P implies Q. Don't ask me why. It is just known that P implies Q is true. Is that okay? And then the second thing we also know is P and R is also true. All right? So this is known. These are things that are you are told that are true. Okay? And then my phi is going to be, I'm just going to say, what about Q and R? Okay, do we know whether Q and R is true or not? Okay, that's the question. So this is the theorem. This is basically what is given to you. And the question is, well, how do we apply all of those things that I just talked about to prove that phi is in fact a theorem? Okay, we know it's a theorem because we actually showed this small theorem a little bit earlier. Okay, so if you have studied my notes, okay, you look at this and go like, well, haven't we proven this already? Yes, we did. Okay, but not using this technique. So the whole idea of today's this exercise here is really to use the technique of CNF resolution and proof by contradiction to prove a theorem that we have already proven using a direct proof. So this way you can kind of get an idea of, oh, we can go for a direct proof sometimes, but we can also go for a proof by contradiction at the same time. But you can also start to appreciate how general this approach is. Okay, so the first thing we need to do is to say, okay, we want to turn psi into a CNF. And the question is, well, it doesn't look like a CNF right now, so how do we turn it into a CNF? All right, so we'll go ahead and get started here. So we got P implies Q and P and R. Okay, so the first step I'm going to do here is to get rid of the implication. So the implication becomes not P or Q, Okay, and then we can use, let me see, it's called the associative rule to remove the parentheses around P and R, because we just have a whole bunch of ands. Okay, the parentheses here really do not matter all that much. So we have this, and just go like this. Okay, is that in CNF right now? It's already in CNF, which is great. Okay, so that means I actually do not have to do much other than changing the implication into not the first part and or the second part. Are there any questions about why it is already in CNF? Okay, a variable by itself is a disjunctive term already. Yes.
So if you would just change the implication,
Uh-huh.
having P and R together would not be CNF?
If I were to change the implication,
Like just keeping the parentheses around P and R.
well, it would still be in CNF, but it's because now you have in that case, your conjunction here is ending with something that is not disjunctive, so it would not fit that kind of strictly. It would not fit that requirement. So you have to remove those parentheses. Now you truly have a conjunction of disjunctive terms. Okay, all right. So that's psi, pretty easy to deal with in this case. Now we look at phi. Okay, so phi itself does not need to be turned into CNF because it's already a CNF, but we don't need phi as a CNF. We need the negation of phi as a CNF, because what we need to do is to combine the negation of the theorem that you want to prove with the facts that are already known to be true. So we need to negate it first. The negation of phi is the negation of Q and R, okay? And we apply De Morgan's law. So anytime you have a negation on the outside of an operation and the inside of the operation is either an and or, you can apply De Morgan's law. De Morgan's law is kind of like the distribution of the negation into an operator, but by doing so, you also have to change the operator itself. If you had an and, it becomes an or. If you had an or, it becomes an and. So to apply De Morgan's law in this case means we now have not Q or not R. Okay, and that is CNF. Now, it's an awkward kind of CNF because there's no and whatsoever. So you go like this, well, why would we call this a CNF? If you really want to insist and say, I want to see that and operator, are you now convinced that it is a CNF? Yes? Okay? So the same thing applies to the disjunctive terms. The disjunctive term P doesn't sound disjunctive at all because P is just P. Okay? Where's the or? Well, if you really want to insist and say, I want to see that or, well, go ahead and say P or 0. Okay? And then same thing for R, say R or 0. Now you can convince yourself that oh yeah, it's a disjunctive term now. But it really doesn't change the meaning from before. Okay? So are we good so far? Okay? How psi becomes CNF and how not phi becomes CNF. Is that good so far? All right? Okay. So now what we need to do is to make what I call a super CNF, which is nothing more than the combination of psi and not phi. Okay? So now we look at psi and not phi. So if you convert psi into a CNF and a not phi into a CNF, the conjunction of those two is automatically a CNF. Okay? It kind of makes sense, right? Because each one is a conjunction of disjunctive terms. So when you have a conjunction to connect both of them, then you just have more disjunctive terms, but they're all still connected by a conjunction. Is that making any sense? Okay? All right, so what is that going to look like? Now, this is where copy and paste really comes in handy, but since I don't have that, well, I do, but I don't want to do that. So I'm going to rewrite the whole thing. So not P or Q, and P and R, that's just, psi itself, it's coming from this part here. And then we have the other part, which is not phi. So not phi is not Q or not R, just that by itself. So now we have a single CNF that combines psi, which represents everything that you are told to be true. Okay, so don't ask why those things are true. And then we also have the negation of the theorem that you need to prove, which in this case is not phi. Now they're all laid out, in one single CNF. So are we good so far? Mechanically speaking, are we okay at this point? We good? All right. So here comes the last part, which is proof by contradiction. So in order to get to a contradiction, what we're going to do is we apply resolution. In the application of resolution, we are looking at the disjunctive terms, and we ask the question, can we find two disjunctive terms where one has the not negative version of a variable and the other one has the negative version of the same variable? So we're just visually looking for that. Okay. Now, if you want to do it sequentially, like in a very systematic format, then you fix the first one to be the very first disjunctive term, and then you just move down the list and see which one can resolve with it. Okay. On the other hand, some of you can just kind of eyeball and go like, yeah, we got this, and we got this, and so on and so forth. I personally prefer the more systematic way, so this way I don't miss something, that may not be obvious. So I'm going to use a color here to kind of code, which two I'm looking at and the term that allows them to resolve. Okay. So as I said, I always start with the first one, but as it turns out, I have one resolution already. The reason why we have a resolution is because this term resolves with that. One is the negation of P, the other one has a non-negative version of P. Is that okay? So now we can say, okay, oh, I got a new subscriber. Nice. Okay. All right. So the nice thing about resolution is everything that you make out of resolution can be added to the CNF. In other words, your CNF can get longer and longer and longer, but it still carries the same meaning as before. So that means, this time, by resolving those two terms, so resolution is basically concatenation by dropping one of the variables. So in this case, I'm concatenating this disjunctive term with this disjunctive term, but I can get rid of P in both cases. So what do I have left? Q by itself. Okay. So now we got Q by itself. All right. So since I mentioned a little bit earlier that I like to go, in a sequential manner, so let's find out whether the first term can resolve with the third term. Can this term resolve with R? Nope, cannot, because we cannot find a variable that appears on both sides where one is negated and the other one is not negated. Can the first term resolve with the last term? Nope, cannot resolve. Okay, so we're really kind of done with the first term at this point. So now we look at the second term, and then we ask, well, what can it resolve with? If you go down the list, you can see that the second term really cannot resolve it with anything, because P cannot resolve with R. They don't even share a variable. Okay, not possible. P cannot resolve with not Q or not R. Once again, they do not share a variable. P and Q also cannot resolve. Once again, they do not share a variable. So that's a dead end. Then we look at R. Okay, what can R resolve with? We don't have to go any earlier, because if it could resolve with any of the earlier terms, we would have found them already. Okay, so this is a very systematic way to make sure that we only look at every single pair that we have not explored yet. So we look at R, and then we look at not Q or not R. Hey, we got an application here, because R is the common variable. It is not negated on one side, but negated on the other side. So once we resolve, what do we have left? Just not Q by itself. Okay, very good. Okay, so let me just use a highlighting mechanism here to highlight that we are resolving this disjunctive term with this disjunctive term. And specifically, what we're doing is we find that this has R, this has not R, and that is what is allowing us to perform resolution in this case. So after the resolution, okay, this is going to be quite boring, but it's not going to be, we won't be doing this much more because we are almost done here. Okay, so after the resolution, then we have one extra term here, which is not Q. It's all right? Okay, so you look at these and go like, now I could go kind of the systematic way and then ask further questions of can we resolve not Q or not R with Q? Yes, we can resolve that and end up with not R, blah 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 blah. But I think many of you already spot that we have a contradiction already. We have Q and not Q. Okay, so but we want to get to the end result using resolution. We are not just going like, oh, Q and not Q is a contradiction by itself. No, we once again applied resolution. Okay, because Q is on one side, not Q is on the other side. But what we might be forgetting is Q is really the same thing as Q or false. Not Q is actually not Q or false, right? So when those two concatenate, we have the false left. Okay, so as a result, when I resolve Q and not Q, and the term that allows the resolution is quite obvious. Okay, it's the entire thing. But the end result of this, oops, wrong color. So the end result of this is we got this and P and R and not Q and not R and Q and not Q and false. But once you have one false in a gigantic conjunction, the entire conjunction is false. And now we have our contradiction. All right? So we have a contradiction, which means, okay, so if this is a question in an exam, and you mechanically derive everything like this, you'll get most of the points. Okay? But you're not going to get all of the points. Because what does that mean? Okay? You understand the mechanical stuff. But what does it mean when you get to contradiction? You have to tell me, because there's a contradiction, when you combine psi and the negation of the theorem that you want to prove, this shows that the theorem is actually a consequence of psi. Okay, so you have to mention that. Okay, so now you have to mention, as an answer, you have to say that because psi and not phi implies false, which is the contradiction, then you say that as a result of that, phi is a theorem. Another subscriber. Yep. Oh, I can see how that can be a confusion here. Yes. So this is false or zero. These are all. I can see. This is a zero, and that is phi. Okay, so let me change this to a bigger zero here. Yes.
Also wanted to know, so did you say it was also okay if instead of conjuncting on the result of the resolution to the end, if we just like whittle down?
Yeah, you could do it that way too. So you can use kind of like a graph, to say which two resolve to this, which two resolve to that, and then eventually get to zero if possible.
Well, I was going to like just circle them and then put the new disjunction.
Yeah. But it would be best, even if you choose that format, it would still be nice if you can identify which term allows the resolution to happen. Yes?
I was just a bit confused on resolution. I noticed that there's not P for Q as well as not Q or not R.
Yeah.
Couldn't you use resolution on that?
You could.
Oh, you could?
Yeah, you could.
We just didn't.
We just did not, because I was going for a very systematic way of finding pairs to resolve, except for the last step.
Okay. That makes sense. I was just
Yeah.
confused on why you didn't.
Okay.
I guess that makes sense. But you could, though.
Yes, you could.
Because I was looking and it looked like it fit the formula. So.
Yes. So this can resolve with that. So you basically get rid of Q, and then you have not P or not R left. So that will be the new term that you're generating. Yep.
So if we get to the line where you have Q and not Q, would you take points off if we just said the whole thing is zero instead of applying resolution like you did?
Don't skip that step.
Okay.
Because the point is, resolution is the only mechanism you need to derive the false at the very end. You do not need to know, in Boolean algebra that, Q and not Q, leads to zero, because you're just applying resolution to do it.
So are we not allowed to put like 4 zeros in there as well, so that we can see when the resolution, like where the resolution is?
You can put in the or zeros.
Okay,
Yeah. Yep.
okay.
Yep. So do we have any questions about this particular application of resolution? Yes.
Could you do more examples if possible?
The notes actually has one example too. So did you have a chance to read through that?
No.
Well, that would be the next thing to do, wouldn't it? Okay. All right. Because this example is different from what I used in the module. So in the module, there are two examples where one resolves to contradiction and the other one does not. Yep.
So is it possible we have one more to here?
Hmm?
One more.
One more?
One more example.
Okay, so if you're asking for one more example, it means one of these steps you're not quite clear on. So instead of giving you one more example, maybe I can help you clarify which step is causing the confusion.
So the sign is with the logic function before any of symbols like R or P or something like that. That and or, is it effective to the maybe we can R process or not? It's been, see, right now we removed R and not R, and before not R in second line is one or.
Okay, which line is the second line?
Second, this one. Yeah.
Okay, this is the second line.
Yeah.
Okay, what about it?
We have R and not R.
We have R.
And
This is R.
Yeah.
And the not R is over here.
And before not R, we have one or.
Yes, this or.
Yes. So if we
It cannot be, because that would not make it a not that would not be a conjunctive normal form. So you have to understand what is a conjunctive normal form first, because that restricts what we can actually have inside the expression. Yep.
Got it. Thank you so much.
Any other questions? No other questions? All right. So if there are no other questions, I'll give you another example, where, things don't work out, okay? All right. So I'm going to use about the same thing. We'll use the same psi, but we'll have a different theorem. So because it's supposed to be a new problem, I'm going to start with, psi would still be the same. Okay, P implies Q. Okay, so for some reason we know that is true. And we also know that P and R is true. Okay, so this is the same as before. And as you can probably expect, to turn this into CNF, pretty easy. We just repeat the same steps as before, turning the implication into an OR, which in this case is already a CNF. And then we just take away the parentheses surrounding P and R. So now we have our CNF. Psi is a CNF. But this time our phi is going to involve a different variable, okay? And we just throw in a completely independent variable here that has never been mentioned in psi, okay? Which is a pretty clear indication that we might run into some problems, okay? So we just say that, psi says, T, Q, let's make this kind of a little bit longer, okay? So Q and T is our phi, okay? So in other words, I'm asking a question, okay? Do we know that Q and T is guaranteed to be true if psi is true? That is the question I'm asking, okay? Go like, well, we don't know, okay? And so let's try to prove it. So that means we have to look at the negation of phi, which is the negation of Q and T. We apply De Morgan's law just like last time, and now we end up with not Q or not T. That is our disjunctive normal, CNF conjunctive normal form of the negation of the theorem. Kind of like last time, okay? So when you look at the mechanical aspect, isn't this really the same thing as last time? Well, so far so, yeah, pretty much. Except for, T was never mentioned in psi, okay? So now we want to prove or disprove this particular theorem. So what we do is we combine psi and not phi into one single CNF, okay, which is just a concatenation of everything that we have. So P or Q is here, P is by itself, R is by itself, and then we have this new term, not Q or not T, which is our last disjunctive term in our CNF. Okay. So now we look for ways to do the resolution. So this time we'll do it your way, instead of appending all the derived expressions. Okay, so we'll do it kind of the same way as last time, except it is formatted slightly differently. So we identify that these two can resolve. Okay, so we just kind of use pointers to say that they resolve. But even if that is the case, I still want you to help me identify what term allows that resolution to happen. Okay, because in the test, what I'm testing is, do you understand resolution? So unless you have something on paper that shows that you understand what resolution is and how to apply resolution, I cannot give you points. Yep.
So do you mean, when you say term, do you mean the whole disjunction or just which part of the disjunction?
So in this case, the arrows are pulling the entire expression, but the red line, which you can use other ways to indicate, is identifying which part of it allows the resolution to happen.
So you prefer to say like both?
Yes.
Okay.
Yep. So after this resolution, P is going to disappear, and we have only Q left in this case. So we got Q here, okay? And then you look at this, and last time I missed one of those, and this time that can apply too. So we will take a look at this term and this term, okay? They can resolve too. So when these two resolve, you kind of have to have a different color or different way to tell me, which two terms allow these to resolve. So we have not Q here, we have Q here. That is what allows these two disjunctive terms to resolve. So after the resolution, we have everything left except for Q. Q disappears. So we have not P or not T left here. Okay. Are we doing okay so far with how we apply resolution? Okay. So we have two resolutions so far. Do we have any other ways to resolve? Okay, let's try to do this kind of more systematically. Yeah, we do. We got this Q and then we got this not Q. So those two can resolve, right? So we take this here and then we take that over here, okay? And now we need another color. I'm going to use orange. So we have this Q resolving with this not Q, and the result is only not T is remaining. Okay, cool. Do we have any other ways to resolve? Huh? Sorry? R? Well, how do we get rid of R? Not T and R. Not T.
So your appended equation down at the bottom is R and not T.
R and.
Because you did resolution twice, so you got rid of two formulas, and then not T ended up staying. But
Yeah.
we never got rid of the R, so that's what I'm asking.
We never got rid of the R. The R is still here.
Oh, okay.
Yeah. So the R is still here. So our actual full version of the CNF right now would be what we had already plus Q, or I should say and, okay, and Q, and not P or not T, and not T. So it has all of those terms. The question is, are there any other ways to resolve? Well, let's do it kind of more systematically, okay? These two, we got it already. These two cannot resolve. These two, we got those already, right? So we got the Q, yeah, we got those. Where did I put it? Yep, right here, okay. This one can also potentially resolve with newer terms. These two cannot resolve, right? Because they both have the non-negated version of Q, cannot resolve. This one and this one cannot resolve because they both have the negative version of P, cannot resolve. These two cannot resolve because they do not have any common variables. So we are really done with the first term. We look at the second term. These two cannot resolve, they do not share anything. These two cannot resolve because they do not share anything, cannot resolve. These two can potentially resolve, but we also got to the same result by another resolution. Because if you resolve P and not P or not T, you also get not T left, okay? So we got the same result even though we did not use the same path, but it's not adding anything to what we already have. So now we are done with the second term entirely. We look at R. R cannot resolve with anything because nobody else mentions R, okay? So that's done. We look at this term, not Q or not T. We go back to the new terms that we have defined here. These two are already resolved here, okay? We are done with that. These two cannot resolve because they both only contain the negative version of T, so we cannot perform resolution. Then we look at all the new terms, right? So we look at Q versus this, cannot resolve, they do not share any variables. Q and not T cannot resolve because they do not share any variables. So now we only got one left, one pair left, which is not P or not T versus not T. They cannot resolve because they both contain the negative version of T. So now we have a conclusion of, I think we are done. We are out of options. There are no further resolutions possible. And yet, we do not have false in the entire conjunction. So what do you think is the result of this? What is the conclusion of this? Huh? It is not a theorem, okay? So in your test, okay, if this is your question, in the test, then what you need to do is to make a conclusion, and then you say, because we cannot resolve to a contradiction, and you can just say false, here, okay, then phi is not a theorem. That is the conclusion. So you have to tell me what the conclusion is and why you think that is the conclusion. So are we good so far with this? All right. So the nice thing about proving theorems in this particular way is you do not have a gazillion of transformations, okay? You don't have to remember, other than the transforming part of putting things into CNF where you need to use Boolean algebra, the actual proof itself does not need to use any Boolean algebra because you're only applying resolutions over and over and over and over again, and then the terminating condition would be one of the two. Either you get false as a result, or you can no longer perform any further resolution. Those are the terminating conditions. Yes?
So we can't have, we won't come across a theorem where we have to prove it's always true and then say it's a theorem because it's always true. It will only be false or we don't know.
So when you combine the negation of the theorem and psi, which are the expressions that are known to be true, if that conjunction leads to false, then you have proven by contradiction that the theorem is actually a theorem. Okay. It follows psi. It follows the things that are known to be true. On the other hand, if you end up with a situation like this, where you do not have a conclusion of contradiction, and it just, because this expression is not guaranteed to be true or false. It all depends on the variables, right? So if you cannot guarantee the conjunction of psi and the negation of the theorem is always false, then you do not have a contradiction. And as a result of that, the theorem is not a theorem. The proposed theorem is not really a theorem. It does not logically follow the things that you were told to be true.
So my last follow-up question,
Mm-hmm.
just to make sure I understand this. If we
Yeah.
negate phi, and then what happens is the equation equates to true, then that whole theorem would not work because the negation is not false.
The negation of the theorem does not lead to a contradiction.
Okay, so
Yeah.
if it's anything but false,
Correct.
then it's not a theorem.
Yep.
Got it.
Mm-hmm.
Okay, I get that.
So are we good so far? Are we tying those three things together? Okay, let me show you what three things we are talking about. So we got resolution. Okay, resolution says only one thing. Okay, it's pretty simple thing that it's saying. So it basically says psi or phi on one side and not phi or rho. This implies psi or rho. This is resolution. Okay? Now, in the general case of resolution, phi doesn't have to be a variable at all. Phi itself can be a whole gigantic, big, huge expression. Okay? As long as it is true on one side and negated on the other side, it will work. But to make things simple, okay, we, in the mechanism of the application of resolution in CNF, we want all of these terms to be simple as it can get. So that's why, we put the additional rule of saying, oh, we want everything to be variables or negation of a variable. So we don't have to deal with complex expressions anymore. This is resolution. What about CNF? CNF basically just says, you have terms, okay, that are connected by disjunction. Okay, and all of these things are connected by conjunctions. So when you look at T, U, and so on and so forth, each one can be a variable or the negation of a variable. Okay, that's CNF, conjunctive normal form. And then we have proof by contradiction. Okay, so then we have proof by contradiction, where it says, okay, psi and not phi leading to a contradiction, okay, this is a big zero, okay, means phi implies psi implies phi. And that's the whole thing about a theorem. A theorem is basically an expression, a Boolean expression in this class, that is implied to be true by everything that is known to be true. That makes it a theorem. So those are the three main ingredients, when we use the techniques that we just mentioned. So this is 1, 2, and 3. The three major ingredients. Yep.
Can you explain or go over Morgan's law again?
The Morgan's law? Sure, absolutely. So let me start a new page after, okay? So the Morgan's law, there are two versions of this, okay? Version A is to say that the negation of A and B is the same thing as not A and not B. Version B says the negation of A or B is really the same thing as not A. Oh, okay, I messed up, sorry. I messed up here. That's an or, and then this time is an and. There we go.
There's one version with and one version.
Yes. Yep. Yeah, De Morgan's law is actually very useful because this is how you can move the negation inside, because what you want to do when you convert a general Boolean expression into CNF is, if you do have negations on the outside, you're trying to push that negation as far as to the inside as much as possible, so that negation eventually only apply to variables and not expressions, okay? And De Morgan's law allows you to do that. So are we doing okay so far with all of this material? Yes?
Actually, I remember in my logic course,
Uh-huh.
in past years, we use some chart like Cardinal's chart
Uh-huh.
to solve this expression easier way or something like
So that is a technique to come up with logic gates to implement a particular combinations of zeros and ones, which is not what we are trying to do here. So we are not trying to come up with logic gates to implement a particular function in Boolean, like, you just give me the entire truth table and ask me, okay, how do we use AND OR gates, to implement that particular truth table? That's not what we're trying to do. What we're trying to do is to prove theorems. Okay, if I tell you these things are true, is that thing over there automatically true? That is what we're trying to get to. Okay, so I think we are ready for the first assignment, connected to CNF. Okay, so what I'll do is I'm going to release that assignment and give you guys some time to work on it. Not in class. I mean, you guys can do it off class. So let me see where the thing is. And I apologize for the confusion because I thought I turned off all of the assignments except for there's one that it doesn't display here. The late submission for is it CNF? Yeah. So it has not been assigned yet. So now I'm assigning CNF. So ignore late submission. Okay. You do not have late submission. You just have CNF. Okay. Oh, my battery is fully charged. All of these notifications, kind of can be distracting at times. All right, so we'll make this due next week. So today is March 6th, so that would make it March 13th, right? So March 13th, and we'll make it due right before class. Oops. Well, I guess that's fine too. Oh, okay. Well,
It's a good validation.
well, in the world of Time Lords, there's no problem with this.
Not all assignments have to start when they first started. It's a really old problem.
There you go. So now you got your assignment. So I will just go ahead and read it to you to make sure that you guys understand what you have to do. So this assignment starts with a particular Boolean expression. Okay, so that's the expression that you start off with. And the objective of this is to turn it into a CNF. That's all. Okay. Seems pretty simple, but it's not. Okay. So you have to know all the tricks, in order to convert it into CNF. Okay. So let me just kind of go over, the tricks that you can do, in this case. Let me switch back to, this will work. Okay. So the tricks are De Morgan's law, but we just talked about it. It doesn't hurt to list it here again. So the negation of A or B is the same thing as not A and not B. So this is my kind of shorthand way of writing and or. Multiplication is the same as conjunction. Addition is basically disjunction. Okay. So this is a quick shorthand. And you can turn in your assignment using the shorthand as well. Okay. And then the other part of De Morgan's law is A and B. The negation of A and B is not A or not B. I use extra parentheses, just to emphasize, what the negation is applying to. But without the parentheses, negation only applies to whatever is immediately to its right-hand side. Okay. All right. So this is obviously one kind of useful trick. Other tricks are like this. Okay. So you have distribution. So you have A and B, or C, and you can do distribution in this case so that you end up with A or C and A or B. Oops. Okay, let's A or C and B or C. Okay, there we go. Which is something that you don't see in arithmetics, right? Because the other version you do, but not this one. Okay. And then you have the other one, which is A or B and C. The whole thing and C is the same thing as A and C or B and C. So distribution works in both directions for Boolean algebra. It only works in one case in arithmetics, but in Boolean algebra, it works in both cases. So are we good so far? Okay, all right. Let's see, what other tricks do you need to know? We got distribution, we got De Morgan's law. Yeah, those are good for simplification. So A or not A is always, you can simplify to true. And then A and not A, you can simplify that to 0. Okay, so that's kind of useful. And then you get, these kind of specialization versus generalization thing. So if you have A already in one term, and then you have in a conjunction, you have another term that says A or B, that simplifies to just A. Does that make sense? It's simplification of some kind. I don't have a particular name for it, but if you go to a logic class, I'm pretty sure they have a specialized name for it. The name doesn't really matter to me. It is just what it does, right? Okay. But are you guys convinced that you can simplify A and A or B to be just A? It kind of makes sense, right? In order for A and A or B to be true, A has to be true, right? But if A is true, A or B is guaranteed true anyway. So that term is kind of useless. Okay? So the reverse of this is when you have a situation where we have A or and then AB, okay? So in this case, you have A being the more general case and then AB being the more specific case, okay? So in order for AB to be true, A has to be true, right? But in the disjunction, if at least one side is true, the whole thing is true. So you might as well just throw AB away because it is useless. So the whole thing simplifies to A again. So in a conjunction, if the overall operation is a conjunction, you can throw away the more general term. If the overall operation is a disjunction, you can throw away the more restrictive term. Okay, that comes in very handy, okay, because it allows you to do simplification along the way, so you don't end up with a term like this long. That makes it kind of difficult to process. Did you miss something? Oh, that's your cup. Very good. We found the owner. That's okay, no problem. There you go. So are we good so far with these kind of specific rules? So from this, okay, can someone tell me what happens to that? You can apply distribution, right? So the trick to understand, how we apply distribution in this case where, attack, you never taught us how to do this. Yes, I did. Okay, treat A or B as one single thing first. Apply distribution like, which one is that? This one, okay? And then don't treat A or B as one thing anymore, expand that. So it's a two-stage distribution, and once you understand how to perform the two-stage distribution, then you end up with AC or BC or AD or BD. Okay? Huh? Yes. I've never heard of that term FOIL until recently. But it's a nested application of distribution, basically. That's basically what it is. Okay? So if that is not complex enough, what about this? It's the same idea. More? Is that called more? But it is, it's basically one more level of nested application of distribution. So so everything still boils down to the basic stuff that is outlined here. It's just that you can apply those things in a nested way to deal with something like this. Okay? Now, some of the hidden rules I haven't really mentioned, like commutative rules, I haven't mentioned. Does anyone know what I'm talking about? Commutative, operations. Left, right can swap positions. Okay? So the only time, with the operators that we have talked about, the only one that cannot do commutative is implication. So that's why the first thing you do is to get rid of the implications. Turn all the might as well just write it here. Yep. So implications are easy to deal with. A implies B, okay, is not A, okay, or B. So the first thing you do is you get rid of implication, because everything else is commutative. How about associative? What does that mean? Left, right, associative, and so on. Yep, you can dissolve parentheses, or you can introduce parentheses if you want to. Okay, you can group things, any way you want, as long as they're all chained by the same operator. Okay, so those are all the basic rules. Okay, yep. Questions? Are there any questions about the homework assignment? Yep. Say that one more time. Implication is, I do not know. You can probably prove it, using Boolean algebra or truth table, but I do not know whether it is or not. I suspect it is, but I'm not 100% sure. Okay, any other questions? So we are getting back to basically algebra, except this is not arithmetic algebra, it is Boolean algebra. Okay? So you don't have to raise your hand, okay? If you have this thought, it is perfectly normal. I'm not going to judge anyone. But I'm just going to be pretending I'm sitting on the other side and go like, why do we have to learn Boolean algebra? I thought, I just want to learn how to code. I want to learn how to program so I can become a developer. And now we're dealing with Boolean algebra. Why do I have to learn Boolean algebra? Why is that important? Can anyone answer that question? Yep, go ahead. Yeah, well, that's one reason. But since I will be writing code myself, I don't need to use Boolean algebra. I'm not deriving anything. Yes.
It's because all programs it's about conditions, and the PC is working by logic gates,
Mm-hmm.
and machine code it's working like that. Assembly code it's working close to that. So it's real language of computer.
Okay. But outside of this class, do you really have applications of saying that through algebraic, operations, this expression now becomes that expression? Why do I need to learn that? Yeah, go ahead.
I was going to say pretty much what he said.
Oh, okay.
Program logic.
Okay, so I'll give you a realistic real-world scenario, okay? So let's just say that you got picked up by Twilio, okay? Because we mentioned Twilio the other day. And you become one of their developers, okay? You're programming the servers, you're putting in code to intercept your SMS, reception, and how to use that to generate traffic to another server and stuff like that, okay? How much code do you think you'll be writing, as opposed to what is the current code base that is already in existence? In fact, what do you think is your first job, okay? You just got hired as a developer at Twilio. What do you think is going to be your first job? Your boss says, Tech, come sit down here, and here is your first assignment. What do you think that assignment is going to be? Do you think it's going to be, Tech, go ahead and design a brand new, class hierarchy, for our API, in a particular programming language? Not going to happen. What's going to be my first job? Say that one time. And what is the best way to get familiarized with the code base that's already in existence? It is the equivalence of giving you a toothbrush and say, go clean that bathroom. Okay? So in coding, in programming, it's called technical support. Okay? Technical support, or you just be part of the chain to handle questions that are coming in, bug reports and stuff like that. Okay, that's one. And you might even be given the task of find that bug. Okay, we got to complain that this interface is not working. Those are the reported symptoms. Go figure out why it's not working and fix it. In other words, you're not going to be writing your own programs for a while. Okay, you won't be writing new code for a while, but you do have to understand existing code. Okay, well, how does that have anything to do with what I just said about Boolean algebra? Just because you do not like to use a certain combination of operators doesn't mean other developers won't use it. So now you see, an expression of a loop, of a conditional statement, okay, in a particular format. And you go like, but what does it mean? This is not how I would apply the operators. So now you have to go through the process. You can do it mentally. You can do it on a piece of paper. And then you just figure out, oh, so it means the same thing as this. Okay, I personally would write it like this, but that person prefers to write it in a slightly different way. But you have to understand that these two are equivalent. They're expressing exactly the same thing. That is why Boolean algebra can actually be practical and useful, even on day one of your job as a developer. Is that okay? All right, so it's a practical skill. In this class, obviously, we heavily rely on that kind of stuff for our homework assignment. But outside of this class, it has applications as well. Are we good so far? Okay. So I'm going to leave you guys with this homework assignment. So our homework assignment is falling a little bit behind because in terms of concept, we have talked about resolution already, proof by contradiction, but your homework assignment is really just turning something into CNF. And trust me, you guys will have fun with this one. It will take you a little bit of time. So my suggestion is to get started early. Even though it doesn't seem like very difficult, get started early. Is that okay? All right. So now that we are pretty much done with propositional logic, let's go back and find out what we should be talking about next. We could get started on predicate calculus, which is kind of the same thing, except it is quantified. But I think you guys got enough of propositional logic for a little bit of time, so we'll rest by talking about something else. Okay? We got 20 minutes, which I think is a good amount of time to introduce the next topic. And I'm not going to get into heavy-duty math or formality, initially. So we'll get into discrete probability. So I'm still following the topics in the same order. So it is important for you guys to read these linked documents or modules ahead of time, okay? Because next week when we do get into the heavy-duty stuff, you probably will benefit from knowing what the terms are, when we introduce those terms. But today, we're not going to use those terms, okay? Today, we'll talk about lotto, okay? Super lotto, okay? We'll talk about lottery. Yay! So the question is, well, when do you know it's a good time to buy a lottery ticket, right? I mean, I'm pretty sure that thought has crossed the mind of many people, some occasionally and some constantly on a daily basis. So, okay, so let's go ahead and understand the rules of the lotto games. There are many versions of those, and the one that I want to talk about is the one that has a super ball. I cannot remember the name. We'll find it. Powerball. That's it. Okay, close enough. All right. So the next jackpot is $381 million. So the question is it a good time to buy a ticket? What are the chances of you winning, and so on and so forth? Okay, so it's math, but it's kind of entertaining, right? Because it does have real life application. So the first thing we need to do is to understand, how do we play that game? So how to play? Is this California Lotto? Yep, it is. Okay, because I want the California version. Step 1, find the Powerball retailer, blah, blah, blah. Okay. Step 2, pick 5 lucky numbers from 1 to 69 and 1 Powerball number from 1 to 26 on a Powerball pay slip. Okay. So the 5 lucky numbers that you pick from 1 to 69 has a few kind of interesting attributes. One is the order does not matter. Okay. If you say, I want to pick the numbers 1, 2, 3, 4, 5, you can list those numbers as 1, 2, 3, 4, 5, 5, 4, 3, 2, 1, 1, 2, 3, 5, 4, and so on and so forth. It's still considered the same combination. Okay, so when you play the lotto game with regard to the lucky numbers, ordering does not matter. Okay, think of it as a set. Okay, ordering does not matter, and guess what? You can only pick one number once. So you cannot say 1, 1, 1, 1, 1. That doesn't work. Okay, okay. So it's kind of like a set. Okay, the lucky numbers is a set of 5 numbers. Okay, order does not matter. Cannot have duplications. The Powerball is kind of on its own. Okay, it is a single number from 1 to 26. Okay, it can be one of the numbers that you have picked already. Okay, that's totally possible. So it is independent to the lucky numbers. Okay, or you can just randomly buy a ticket with whatever is generated. Okay, so that's the second part, step 2. And then we move on to step 3, purchase. And then we have step 4, believe. Okay, and then we have step 5, which is check. Okay, so find out what the actual numbers are, and then you can determine your prices. So we got these prices here. Okay, so if you don't win the jackpot, which means the 5 lucky numbers, they're all matching, and on top of that you also have the Powerball number matching, that would get you the jackpot. But the chances of winning that is 1 in 200 and something million. Okay. I think the jackpot right now is 380 million, right? So it sounds like it's time to buy a ticket, but it's not. I'll explain that later. But you don't have to win the jackpot. Okay, there are other chances to win too. So you can match only the 5 lucky numbers, but the Powerball does not match. Okay, so that's the second prize. and the odds of winning that is quite a bit better, 11 million to 1 or so, okay, 12 million to 1. You can also win another prize, if you match any 4 of the 5 lucky numbers and the Powerball, or just any 4 of the 5 lucky numbers, and so on. So there are various ways to win something when you buy a lotto ticket. So now the question is, how did they figure out these numbers? How did they figure out all those numbers? So that's one question. And then the second question, which is more important, is today a good day to buy a lotto ticket? So the lotto ticket, the jackpot, is $380 million or so, okay? Which means on the average, okay, if you just have average luck like everybody else, you buy a ticket, and then when you look at the return, it's actually more than $1. Okay? So it seems, until you take into consideration taxation. Uncle Sam needs his cut, right? So if you have an income of $380 million, what do you think that will place your tax bracket? Yep. So you don't want to take your money. Do they let you take your winning money not in a single lump sum and take it in like smaller chunks? Depends on, okay. But the distribution of $380 million cannot be very slow. So even if you take $1 million a year, it will still take 380 years. So let's just say that it's one of you guys, okay? I'm much older, so I cannot really take the distribution in like 38 years, okay? So let's just say that you say I'm still young, I want to take the distribution in 38 years. I don't know. I'm just playing different scenarios, okay? So if you have $10 million as an income from a lottery, that would put your tax bracket pretty high, both in California and also in federal, right? So that means you may not be making money. I mean, on the average, you're not making money. Okay, if you do win the jackpot, yes, you would still be making a lot of money. But but on the average, it's not the case anymore because you don't really have 380 millions in your pocket. Okay, once you deduct the portion that the taxation part. Okay, so let's double that. Okay, so let's say the jackpot is now $760 million. Okay, I mean that should be enough to cover taxes and stuff, right? But now you have a different equation because multiple people can buy the same number. Okay, and you go like, that's unlikely to happen. I mean, there has to be a lot of combinations, right? I mean, the chances is 292 million to 1. The entire population of the United States is 300-something million. Okay, so you go like, it's pretty unlikely. And I can tell you it is very likely. Why? Because if the jackpot is high enough, then somebody is going to go to the bank and say, I want to take out a loan so I can buy every single number there is. There's a lot of numbers, but you're guaranteed to win too. Don't you think? Yeah, you'll be buying 300 million tickets, but you're guaranteed to win, and the jackpot is 760 million. So it sounds like the math is going to work out, except everybody has the same idea. You end up with like 20, 40, 800 people buying every single number there is. And guess what? You now have to share your jackpot with those 80 people. And now you don't have enough money to return to the bank. And then you have to declare bankruptcy and all kinds of bad stuff. So the model, does not take into consideration, and there's no easy way to model, how many people will play depending on the jackpot. Okay. Now, if you have a jackpot that's really like that, like $150 million, then very few people is going to play. It's like, come on, it's not even, the odds is less than, I mean, payback is less than the odds. Okay, so nobody's gonna play, or very few people will play. But as soon as you hit like 400 million, okay, suddenly more people will go like, oh, because of the psychological factor, more people will start to play. But that number, okay, let's look at it as a function, right? So the function that maps the jackpot to the number of people who are going to play is somewhat unknown, okay? It's not something that we can actually mathematically model. We can look at past history. I mean, the website actually does keep track of that too, but it's not something that we can easily model. So that's kind of the whole idea of playing lotto. Now, if you look into, they actually keep track of a lot of interesting facts too, past winning numbers, for instance. So when you click on past winning numbers, okay, they actually show you, you can pick one. It actually shows you the frequency too. It shows you how many tickets correspond to each prize. So you can see that in the previous run of this particular lotto game, nobody got the jackpot. Nobody got even this one. 5 people got 4 lucky numbers and plus the Powerball and so on. And this is the payoff. So you can also see the payoff of 5 people for $14,000 each is a drop in the bucket when it comes to the actual jackpot. Okay, so even though on the list it's third on the list, but when you look at the drop off in terms of payoff, it's like insignificant. Okay, so the total payoff, oh, they don't show that, but they can show the winning tickets. So from these numbers, if you understand statistics and counting and probability distribution, from these numbers you can actually work out how many tickets was sold. That is pretty cool, because now you have a past history of how many tickets are sold, based on the jackpot. So now at least you have some kind of a model to say, oh, the jackpot is now $300 million. How many people are going to play? You kind of have some idea. Is that okay? So getting back to the odds, okay, so let's go back to the previous slide or the previous web page. So now the question is, how do we know how they came up with these numbers? How is the odd calculated? What do you think? Yep. Yep. Yep, exactly. So this is the number of possible tickets. So how do we come up with that number? Well, think of it this way. Has anyone actually seen, how they draw the balls out of a cage in a lotto game? Yeah. Okay. So originally you have a cage with 69 balls. Okay, one number for each ball, right? So you draw one out. Okay. So the first ball that is being drawn, how many possible numbers are there for the first ball? 69. The second one, 68. And the third one, and so on, right? So you can now say that, oh, if ordering is important, then the total number of ways to draw 5 numbers out of 69 would be 69 times 68 times 67 times 66 times 65. Does it make sense? But that's counting the cases where ordering is important. So if you draw the balls in the order of 1, 2, 3, 4, 5, it is considered different from 5, 4, 3, 2, 1. So how do I get to the number where ordering is not important? Well, then what you look at it, then the way you look at this problem is you say, okay, we have 5 numbers drawn, okay? 1, 2, 3, 4, 5. How many different ways can I rearrange 1, 2, 3, 4, 5? So that it becomes 1, 2, 3, 4, 5, 1, 2, 3, 5, 4, 1, 2, 5, 4, 3, 1, 2, 5, 3, 4, and so on. How many ways do you think you can do that? It's 5 factorial, right? Because you have exactly 5 balls, okay? So who can be the first one? All of these can be the first one, so there are 5 choices for the first one. Once you have chosen the first one, there are 4 choices for the second, 3 choices for the third, two choices for the fourth, and the last one, hey, we don't have a choice anymore. Whatever is left is going to be the fifth ball. So you take 69 times 68 times 67 times 66 times 65, you divide it by 5 factorial. That becomes the total number of combinations of the 5 lucky balls. Does that make sense? Because you have eliminated all the double counting because of the ordering, part. Then you have to multiply that number by 26, because the Powerball number is completely independent to the lucky numbers. So that means that you just multiply 26. Okay. So let's just use this opportunity to check whether that math works out or not. And one tool that I find really helpful to work out these things is just a spreadsheet. I don't really like to use a calculator. I like to use a spreadsheet. That's my writer. Okay. Let's go to a spreadsheet again. Calc. There we go. Okay. So in a spreadsheet, we are looking at, okay. Okay, we'll just kind of work out the math entirely using what we just said, okay? So I'm not going to use any combination or permutation kind of stuff here. So 69 times 68 times 67, 66, and 65. So this is the total number of permutations of picking 5 things out of 68, which means ordering is important. 1, 2, 3, 4, 5 is considered different from 5, 4, 3, 2, 1. So we have to divide this number by 1 times 2 times 3 times 4 times 5, which is basically saying, if I have 5 things, how many different ways can I rearrange those 5 things? Okay, so this way I remove all the duplicates. Okay, and then I have to multiply this to 26, because we have 26 possibilities for the Powerball, which is entirely independent to the other 5 numbers. Does it make sense? Okay. So let's press the enter key. Does that number look familiar? Yep. That's how they came up with that number. So next week we'll be focusing on these topics. Okay. So we'll talk about what is a combination, what is a permutation. If you know how many things you have available and how many things you have to choose from those things, what is the equation to calculate the counting part of this. Okay, that's going to be the focus of next week's lecture. And as I said, in addition to starting to do your homework assignment that is due in a week, you might want to spend some time to read ahead of me, so that you understand the terms, you understand the concepts and the applications. And if you do have questions from reading the notes, bring those questions in class. Okay. So I'll see you guys on Monday, and have a nice weekend.